Hi, I'm Maria Hesberg, and my presentation is on the physics of optics and vision correction. And I chose this topic because I'm a biology major. So here's a picture of how light rays naturally hit the retina of someone with perfect vision. So when light hits the retina, it sends a signal to our brain. And if someone has perfect vision, then light rays converge and focus the image on the retina. If someone doesn't have perfect vision, then the light rays converge either in front of or behind the retina, creating a blurry, unfocused image. So this is an example of contacts, and these are my brother's contacts. I have almost the exact same prescription as him, but here it says that he has negative 0.75 diopters in his left eye, and in his right it's negative 1.25 diopters. And this is his corrective lenses for his nearsightedness. So when eyes are too long, someone is nearsighted, and it means they can't see far. So the image will get focused in the middle of the eye, right here. If your eyes are too short, then you're farsighted and you can't see near, which means the image gets focused behind the eye, as in right here. How do lenses and contacts correct our vision? So lenses and contacts basically create a virtual image. A virtual image is an optical image formed from the apparent divergence of light rays from a point, as opposed to an image formed from their actual divergence. So, not a real image. Lenses bend the light coming into our eyes that move the image we are seeing. This allows us to focus the virtual image so it's upright on the retinal surface and comes into focus. So nearsightedness is corrected with a concave lens. That means the lens folds inwards, and then they're able to see what looks like a cat. They're able to see the cat because it's now focused on their retina. And then farsightedness is corrected with a convex lens. And here it's folded outwards so they can see the cat near, which is pretty close to them, and that can be focused on their retina. So this is how we find someone's prescription based off of how far they can see. In nearsightedness, the far point is the farthest point that a person can see things clearly. A diverging lens is used to cause an object that is very far away, using infinity to mean it's relatively far, to bring the object within the far point so the person can see the image clearly. So here we have object distance, which is infinity. We have the image distance, which is 50 centimeters, and the far point is 50 centimeters. So this person can see anything within 50 centimeters, and then beyond that to infinity, they have trouble seeing. So how do we find the prescription? In order to find the prescription, we need to find the focal length of that lens. The focal length is the distance between the center of a lens or a curved contact and its focus. So here's the focal length, the object distance, and the image distance, and we plug all those in to the equation and solve to find negative 50 centimeters. The distance, this is negative because the image is in front of the lens. And 1 over infinity crosses out to 0 because any number divided by infinity is 0. So negative 50 centimeters is the focal length of the lens, but you need the power of the lens to write a prescription. Oh, sorry, spelling error. say prescription. How to find the power. So we take that negative 50 centimeters and we need to find the power. Power is 1 divided by the focal point. So we take negative 50 centimeters, we have to convert it to meters and take the inverse of it to find negative 2 diopters. So units for power is diopters. And if you go to the store and see glasses labeled negative 2 diopters and your focal point is 50 centimeters, then those glasses will help you see things clearly that are far away. So back to the contacts. Here I added the focal length. I figured out the focal length by taking the inverse. And my little brother, he in his left eye can see anything 133 centimeters in front of him, but anything further he has blurry vision. And then in his right eye it's 80 centimeters. And the negative is just there to show that the image is in front of the eye. So then for a far-sighted person, you have to find the near point, which is the closest point an object can be placed and still form a focused image on the retina. Sorry, another spelling error. A converging lens is used to cause an object that is very close, and it brings the object within the near point so the person can see the image clearly. So here we have the near point. Here's the object. The object is 25 centimeters from the eye, which is too close for the eye to focus. So when they wear this lens, then it changes the object to appear right here, and then they're able to see it clearly. So to find the prescription, we again need to find the focal length, and it's different this time for the object distance and image distance. So the object distance is 25 centimeters and the image distance is negative 50 centimeters. So ultimately the focal length, once we solve it, is 50 centimeters or 0.5 meters. So again, we need to find the power. So here we have the power, and back here we solved for this equation and we ended up getting a positive 50 centimeters, whereas for a nearsighted person we got a negative 50 centimeters. So this changes the power because now the power, when we take the inverse of 0.5 meters, it's plus 2 diopters. So this means that if you go to the store and see reading glasses labeled plus 2 diopters, this means your focal point is 50 centimeters, and those glasses will help you see things far away clearly. And that's my works cited. Thank you.